Hi, everybody. It's time to wrap up our discussion about extrasolar planets. We've done all the work to understand the ways that we detect extrasolar planets, and we even talked about how we use the transit method and the radial velocity method, and we've discovered over 4,000 extrasolar planets so far. That number grows every year. Since I did this last semester, I guess, the number was about 300 higher. So we're adding a couple hundred per year to our list of extrasolar planets. And in that, we are starting to discover the vast diversity of not only planet types and how many of each planet type, with good statistics on how many, say, Earth like planets there are versus how many Jupiter like planets there are. But we're also seeing the design of extrasolar planetary systems. And all of this is helping us understand not only our vast universe, our galaxy, and the possible planets that are out there, but it's giving us the crucial information we need to understand how planetary systems form. So let's take a look at the diversity of extrasolar planetary systems. This is just a graphic. I wish they'd make an updated one. It's just an artist's impression of a large variety of extrasolar planets that have been discovered to date. But out of everything that's been discovered, and this plot is a little bit old, what it's showing is the orbital period. So this is number of days. Notice it's a logarithmic scale. So 1, 10, 100, 1,000 days. So about three-ish years. And then this is size relative to Earth size. So 1 would be Earth. So if we went to 1 year, 365 days, and then uh, the size of the Earth, then we would find the Earth. And what this is doing is they've mapped out the different types of planets that we've discovered. And they even have included some information about how each one was discovered, what technique, and in some cases, whether it was Kepler or not, these telescope that was doing all the discovering of the extrasolar planets. But what have we discovered? Well, we see a lot of different types of planets. We see the three that we see in our solar system. So we see gas giants, although really our gas giants are kind of cold. So we see cold gas giants. We see Earth like terrestrial planets. And we see cold ice giant planets. But we see a whole host of other types of planets as well. Something that we're about to talk about a lot are a so-called type of giant or a type of gas giant planets that we call hot Jupiters. These are Jupiter-sized planets that have orbital periods less than 10 days and are located ridiculously close to their stars. So they're Jupiter gas giant planets, parked in orbits closer than Mercury's orbit is to the sun. So they're parked right next to their stars, making them very, very hot. And they're Jupiter-like gas giants. So we call them hot Jupiters because astronomers are good at naming things. We see Neptunes that are also hot. So a Neptune is the generic term we took for ice giant planets, just like Jupiter is the generic term we took for gas giant planets. So hot Neptunes would be ice giants that have moved in close and are now parked close to their stars. We also see a class of planets that we would call subgiants. And many of these would include what we also call super Earths. We are still working out all the different types of planets out there. But one of the more exciting ones that I once attended a conference about is so-called ocean worlds. Worlds that have roughly equal amounts of water and rock and metal. Well, smaller amounts of metal. But they would be much, much larger than the Earth, 2 to 3 times the mass of the Earth, maybe 4 times the mass of the Earth, and would have formed where they have so much water that would be thousands of kilometers of water as an ocean on the entire planet. And if they're located close to the star, that would be liquid water. If they're located far away from the star, that would be a frozen world, but likely a liquid water ocean underneath. So so-called ocean worlds. And then with the terrestrial type planets, not only do we have like these ocean worlds, which are somewhere in between terrestrial and say ice giants, but we also have super Earths. Terrestrial planets very similar to our Earth, but much more massive than the Earth. Say 1.5 or 2 times or 3 times more massive than the Earth, but otherwise just like the terrestrial planets we see in our solar system. And we have strange worlds that we call lava worlds, which are just terrestrial planets that are much closer to their host star than, say, Mercury is to our sun. So if we were to move Mercury in closer and closer and closer, so it's parked right next to and it orbits right next to the sun, Mercury would be what we'd call a lava world in that case. And why do we call these lava worlds? Well, they're so close to their stars that their surface temperatures would be hot enough to melt rock. So you would have a surface of molten rock, which we call lava. And yes, we have observed planets like this. They would be right here on this plot over here. And one of the cool things about it is people have built models, and these planets should form clouds of silicate vapor that would then condense just like rain droplets condense in our clouds, except it would be condensing rocks, and these planets might rain rock. Could you imagine stepping outside on a lava world? Let's imagine you're not going to get burned up instantly, but then you step outside and like, today is a pebble rain day, and you're just getting pelted with pebbles falling on your head. So a lot of different varieties of planets, more than we have, and it's sort of we can almost see this nice continuum of types of planets. And in each case, we have like the hot and the cold versions of them. And I just want to give you some additional information. So what do we know? What are our numbers? So far, we have 4,292 confirmed planets. 1,460 of them are Neptune-like. 1,341 are gas giants. 1,322 are super Earths. 163 are terrestrial, and 6 have not really been classified yet. These are the statistics on what method was discovered. What's really exciting is imaging. So direct imaging is becoming a more popular way of detecting extrasolar planets, as we have things like the VLT telescope that can do super high angular resolution. We could add a component to the telescope that blocks out the starlight and starts looking for the dimmer planet next to the star, usually in the infrared, because planets only reflect, planets that we're used to reflect visible light. But the Earth is giving off tons of infrared radiation. So if we look for planets in the infrared, we could actually see the light, the thermal light given off by a planet. And then we could directly image the planets. And we can use telescopes like the VLT to do that. So that's becoming a more popular detection technique. Okay, so let's talk about what we can use, what we can glean from all of this amazing information about all the possible worlds out there, all these extrasolar planetary systems, and look and see what that implies for the planetary formation process, planetary system formation process. And a very interesting class of planets that has a huge implication or consequence and revolutionized our view of how planetary systems formed were these hot Jupiters, because they took us by surprise. The very first extrasolar planet we discovered, 51 Pegasi b, in 1995, the first extrasolar planet in orbit around a main sequence star, is a hot Jupiter. What is a hot Jupiter? So right here, we just have a variety of systems. Here's our solar system with the relative positions of Mercury, Venus, Earth, and Mars, and relatively scaled in size. The sun is not scaled appropriately. I've put a line right here to show the orbit of Mercury. Here's 51 Pegasi. Here's 51 Pegasi b, a planet that's 60% the mass of Jupiter and orbits the star much, 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 much closer than Mercury orbits our sun. So that is a very hot Jupiter. And then here's another example. These would be hot Jupiters as well, although a little bit less hot, but still pretty hot. Mercury is hot. So we have all of these hot Jupiters. And we were surprised by this because everything that we know and physics itself tells us that you can't form a Jupiter-sized planet this close to a star. So if you can't form a planet here, if you can't form a hot Jupiter, or you can't form a Jupiter-sized planet as a hot Jupiter, what does that mean? It gives us this implication that planets must migrate. And what do I mean by planetary migration? So you form a Jupiter out, say, about where Jupiter is, and then through the planetary formation process, that Jupiter-sized planet will naturally move inward, migrate inward, decrease its semi-major axis, and move closer to the host star. It's the only way we can end up with hot Jupiters. And the fact that we see so many hot Jupiters out there, that this is a common consequence or a common system that we observe, tells us that planetary migration must be common in the planetary formation process. The question is, why did our Jupiter and our Saturn, our gas giants, stay where they are? Or really, they didn't stay where they are. Why didn't they migrate all the way in through the inner solar system? Why aren't they hot Jupiters? And that becomes a very, very interesting tale and some of the fine nuance in the story of how our solar system formed. And another thing that we observe, we can look at all the extrasolar planets, look at their orbits, and take a look at the eccentricity of their orbits. Remember, for our solar system, almost all the planets have an eccentricity very close to zero, nearly circular orbits. The planet that has the highest eccentricity is Mercury, which has an eccentricity of zero point 0.2. Sure, a squashed circle, but only slightly squashed. And 6 of the 8 of our planets have eccentricities less than 0.05. So that is what we thought was the norm before we started to see all these extrasolar planetary systems, that every planetary system will have nearly circular orbits for their planets. However, 80% of all the discovered extrasolar planetary systems or extrasolar planets we have eccentricities greater than 0.1, and over 20% of them greater than 0.5. Very, very, very eccentric systems. Here is a planet. This one's called HAT P13C. Great name, right? Has an eccentricity of 0.666. So it's normal for planets to have high eccentricities, which had us scratching our heads like, okay, why would they have such high eccentricities? And this is actually closely related to the planetary migration. If planets are, as they're forming, are moving around, then they're going to gravitationally interact with one another. Because if you have two planets that get close enough, their gravities are going to significantly tug on one another. And the net result is whenever you have they gravitationally interact, they'll slightly change their orbits. The lower mass one will have its orbit change more than the higher mass one because of inertia, but they'll both end up with changed orbits with a net increase in their eccentricity. We call it pumping up their eccentricities through these gravitational interactions. And since the two planets come close to one another and gravitationally interact and then leave in a different direction than they came in at, we call it a gravitational scatter. And the fact that most extrasolar planets have high eccentricities tell us that gravitational scattering must be a common thing. As all the planets are forming, they must be moving around a lot and interacting with one another a lot. So, 2 new lessons learned from extrasolar planets. Planets migrate, and in this migration, there's a lot of gravitational interaction between them. And I want to show you what a controlled version of gravitational scattering looks like. So this is, and actually I'm going to go back. What I'm going to show you is what's called a gravitational assist. And this is how we design spacecraft so we can use the minimum amount of fuel. And basically we can alter the planet or alter a spacecraft's orbit through a close encounter with another object in our solar system, a planet or an asteroid. And basically we will steal some of its angular momentum to experience a gravitational scatter to speed up or slow down however we need to change the velocity of our spacecraft. We'll do it through a gravitational encounter with another object. So let's look at this controlled version called a gravitational assist, a gravity assist. And this is for the spacecraft Rosetta in pink. And it's interacting with, say, Mars right there, getting a gravitational assist from an asteroid, gravitational assist from an asteroid, and then it reaches its target of 67P Churyumov-Gerasimenko. So we use a series of controlled gravitational scattering events to alter the orbit of the spacecraft. Notice that its orbit is getting increasingly eccentric. And we did it in a controlled way where we actually aimed it so it would encounter the comet that we were trying to hit, 67P Churyumov-Gerasimenko. And we do this routinely. This is a very common practice, especially as we're sending things out into the furthest reaches of the solar system, because we just can't put enough fuel on the spacecraft to get the kind of changes in velocity that we need. All right, so that is the end of Unit 2, Part 1, official material. I wanted to go ahead and share some bonus material though, so this is not on quizzes or exams, but if we're talking about extrasolar planets, let's talk about one of the most exciting things about extrasolar planets, potentially habitable planets that are Earth-like. So what do we mean when we say potentially habitable? We mean that that planet is in what we call a habitable zone for its star. And a habitable zone for a star is the correct distance away from the star so that the planet receives just the right amount of sunlight to warm it up to the point where liquid water can exist on its surface. Water can exist in its liquid state. And of course, it's not just a single distance away, that's going to be a whole range away. So we have a entire habitable zone. So this would be for our sun, and here's our solar system. And we technically have 3 planets in the habitable zone. Venus is technically in the habitable zone, although on the inner edge where it's a little bit too hot, its thick atmosphere heats it up too much, so it can't have liquid water. But if it didn't have an atmosphere, it would have temperatures that would be sufficient to support liquid water. Then we have Earth, which is happily in the habitable zone. And then we have Mars, which is technically in the habitable zone as well, on the outer edge where things are pretty icy. But there are days on Mars where the temperatures aren't that bad. So it's just the range away from a star, the semi-major axis distances away from the star, where liquid water can possibly exist. And this depends on a few things. It depends on the type of star. Brighter stars will have a different habitable zone, a different distance, because you'd have to move farther away for a brighter star, a hotter star. Colder stars, you'd have to move closer in. And then you have to determine like the age of the star, because there are things that are changing with that. So it's the type of star, the distance away from the star, a few other factors like the age of the star, considerations like atmospheric components of the planets themselves. But the habitable zone is a pretty blanket term. Just means that you're the right temperature, the right distance away to have liquid water on your surface. All right, so now that we know what the habitable zone is, let's look at 2 exciting systems. You might be heard about this. You might remember in 2017, astronomers got really, really excited, and because there's news big enough to hit the global news cycle, the discovery of a extrasolar planetary system called the TRAPPIST-1 system, where they discovered seven terrestrial-like planets. Terrestrial planets being Earth-like planets. Earth-like does not mean that it has an atmosphere that we can breathe and has water on its surface. Earth-like just means terrestrial and around the mass of the Earth. So these 7 planets, the TRAPPIST-1 planets, orbit a very different type of star. They orbit a M-type star, one of these really low mass type stars, one where its temperature, or surface temperature is around 3000-ish Kelvin, which makes it so if you looked at that star, it would be quite red. So these planets all they have a red sun in the sky, and they probably have red skies. Kind of weird to think about. And not only does it have 7 terrestrial planets, 4 of those terrestrial planets fall within its habitable zone, which is really, really small. So this is zooming in, all interior to the orbit of Mercury. They have orbital periods of days, and they're tidally locked to their star. But there we have 4 potentially habitable worlds in one system. We got really, really excited about this. And another cool thing that NASA does, I'll try to put a link to this in the README for the week. NASA makes all sorts of cool travel posters for planets, asteroids, and other things. But they also make travel posters for extrasolar planets that you can download. They're free and print them out. This is the travel poster for TRAPPIST-1E. And then there is the very first Earth-sized planet found in a habitable zone, Kepler 186f. And I think this one actually has an official name, although I can't remember what it is off the top of my head. But this was the first Earth-sized planet discovered in a habitable zone. It also orbits a M-type red dwarf star, much smaller than our own. So it would have red skies as well, hence the travel poster over here. We don't know if it has an atmosphere or not, but we have detected it, and it is a system that has many planets in it, many terrestrial planets in it, and one of them is Earth-like and in the habitable zone. Which makes you wonder, how many of these habitable Earths have we discovered so far? So we've discovered one that's going to be Mars-sized, what they might call sub-Terran, sub-Earth sized. 23 that are Earth-sized. 36 that are super Earths, whether they are terrestrial, ocean worlds, or maybe mini Neptunes is unclear. But that gives us a total of 60 as of October of this year that we've discovered of worlds out there that are technically within their habitable zones. Here's a graphic that shows scaled sizes and a list of some of the habitable exoplanets that are terrestrial planets, and they're ranked by increasing distance away from the Earth. So the closest one is Proxima Centauri b, which is 4.2 light years away. Uh, just a hop, skip, and a jump, cosmically speaking, and then there's increasing as we go farther and farther away. Kepler 442b is about 1,200 light years away. All right, so I just wanted to share some of that exciting stuff with you. I hope you enjoyed learning about extrasolar planets. This ends the material for this week. This ends the material for Unit 2, Part 1. Hopefully you feel like you know a lot more about our solar system and all the amazing planetary systems that are out there. I will see you in the next set of videos.